Okay, 10.14 notes is finding Taylor or Maclaurin series. So at the top of 10.14, write FRQ. Why? Because every year there is typically an FRQ over 10.14 or 10.15. Okay, more specifically on Taylor and Maclaurin series. Can you take a function and write it as a series? Okay, so it says Taylor series, if f of x has derivatives of all orders at x equals c, then a Taylor series may be formed that is equal to the function for many common functions. So again, a Taylor series can be representing functions like e to the x, sine x, cosine x. This was all before we had access to a calculator. And so if you recall, Taylor series, which hopefully you have memorized by now, is the summation of n equals 0 to infinity, f to the nth derivative of c over n factorial times x minus c to the power of n. Remember, this can be expanded to be f of c plus f prime of c times x minus c, and then continued on and forever. So like the second derivative, and then x minus c squared, and then over 2, and then over 3 factorial, continued on and on forever. Okay. If c is equal to 0, that is called a Maclaurin series. So we're going to use this concept of Taylor series, and we're going to use it to find 4 common functions. Okay, so I'm going to show you how to find them using e to the x and sine x. And then the table below, you're just going to have to memorize those. Okay, reason for that is if we can memorize the series expansion and the series notation for 4 basic functions, we can manipulate those 4 basic functions to find all types of Taylor series. So the first one is a Maclaurin series for e to the x. So again, I'm just going to substitute c equals 0 into my Taylor series. And then for e to the x, I know that every derivative of e to the x is e to the x. So I have f of x is equal to f of 0 plus f prime of 0x plus f double prime of 0x squared over 2 factorial. Okay, and again, this continues on forever. I can easily plug in f of 0, f prime of 0, etc. because e to the x derivatives don't change. So e to the x is equal to, e to the x is equal to 1 plus x squared over 2 factorial. And if we continue that process, it is x to the n power over n factorial. So again, I'm able to plug in each of the functions because e to the x derivative doesn't change. And since the derivative doesn't change, that means no matter what, when I plug in x is equal to 0, I'm going to get 1. Okay. And so this means that I can write this in series notation as the sum is n equals 0 to infinity of x to the n power over n factorial. And then based off of convergences that we've been talking about in previous notes, I know that this is going to be an interval of convergence, okay, for negative infinity to positive infinity, or you can say converges to all real numbers. Okay, for sine of x, this one's a little different. It's not as simple as just saying all the derivatives are the same. Instead, we're going to have to find all the derivatives. So if we have the function sine of x, that means the first derivative is cosine of x. The second derivative is negative sine of x. And then the third derivative is negative cosine of x. So I would try to do a few derivatives, maybe 2, 3, or 4. Okay, when you're having to write out a series, just to show that you understand what is happening with every term. Okay, then for here, again, we're plugging in 0, so I have f of 0 is equal to 0, f prime of 0 is equal to 1, f double prime of 0 equal to 0, f triple prime of 0 equals -1. So it's going to go back between 0, 1, 0, -1, and continue following that pattern. So if we're using that Maclaurin series to estimate sine of x and plugging in all our functions, function derivatives, and the point 0, we get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, all the way until we get -1 to the power of n times x to the power of 2n plus 1 over 2n plus 1 factorial. Okay, we can write this in series notation as the summation of n equals 0 to infinity of -1 to the power of n times x to 2n plus 1 over 2n plus 1 factorial. And again, based off of convergence, this is going to be an interval of convergence from -infinity to +infinity. So again, from all real numbers. Okay, so think of these almost like proofs. We're proving how we can rewrite e to the x and sine of x using a Maclaurin series. Okay, for these basic functions, you are not going to be required to show these steps. Okay, that is because you are going to memorize the series expansion and the series notation for each one. So what mainly is going to pop up on an FRQ is, let's say instead of asking you to find the series expansion for e to the x, they may have you find e to the 5x. Okay, and from there you're just going to be adding 5 in there. Okay, same with sine and cosine. If you know sine and cosine, then you can find tangent. Okay, sine divided by cosine. So as long as we know these 4, then you should be good. So I'm just going to highlight this box. Okay, you need to have these ones memorized. Okay, which means at this point it's going to be memorizing this for Unit 10 and also the flow chart for convergence and divergence. Okay, so I'm just going to go ahead and write the series expansion, notation, and interval of convergence for each one, and just go ahead and copy it down. Okay, we already did the first 2. Notice with cosine, the main difference is it's going to start at 1 instead of x. And then instead of all our exponents being odd, now our exponents are going to be even. And then this last one, 1 over 1 plus x, we're going to look at something similar on the next example. So these are the series expansions for each. Then the series notations. Okay, and again, notice for cosine, the main difference here is that exponent here. So it's going to be x to the 2n versus 2n plus 1 over 2n factorial. So the even exponents versus the odd exponents. And for the interval of convergence, the first 3 are just going to be all real numbers. Okay, from negative infinity to positive infinity. The only one that is not going to be all real numbers is that last one. And that interval of convergence is only going to be between -1 and +1. Yes?
Sorry, what's on the third row, second one? Is that -0 to the power of n?
-0.
I can't read that.
Oh, is it -1 to the power of n? This part right here?
Yes, that. Never mind.
Sorry.
That just going to be 0 to
Yeah, it's -1 to the power of n. Okay, any questions so far? Okay. So let's go ahead and look at the next example. And remember, it's recorded. You can come back later. Sorry, we have to get through the other notes too. Okay, so the function f of x is equal to 1 over 1 minus x is actually a geometric series. Okay, and I'm going to show you that here. Notice, this is not the same as the one that you're memorizing. The one that you're memorizing is 1 over 1 plus x. Okay. However, there is going to be a connection between the two. So recall a geometric series. We write that as the summation n equals k to infinity, a times r to the power of n. We can simplify that using the formula a times r to the power of k all over 1 minus r, where the absolute value of r has to be less than 1. Okay, since we're doing a Maclaurin series, we know that we're going to be plugging in 0. So this is going to become the summation of n equals 0 to infinity, okay, of the AR to the n power, which if we plug in 0 for k, so right here, okay, what's going to happen here as n is going to 0, sorry, I meant right here, n is going to 0, okay, this is going to become, using that definition, just a over 1 minus r. Okay, we no longer have on the top the r to the n power. Okay, because r to the 0 power would be 1. That's why it's gone. Okay, well, if we're comparing that to our equation up here, this tells us that a is equal to 1 and r is equal to x. Okay. Which means I can expand this 1 over 1 minus x to be the summation of n equals 0 to infinity x to the n power, which is 1 plus x squared plus x cubed, etc. Okay, so when you're looking at this, this is another good one to have memorized. Okay, if you look at the original one, the 1 over 1 plus x, notice it looks exactly the same, but instead it's alternating between positive and negative. Okay, for this one with 1 over 1 minus x, they're all remaining positive, but everything else is the same. Okay, so now these next examples is how you would see them on multiple choice or FRQ. So for 3 and 4, it says find the Maclaurin series for each of the following functions. And so for number 3, it says sine of x squared. Well, we already know sine of x because we have the table memorized. And so I'm going to write sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. Okay, of course, this continues on forever. So if I already know sine, that means I can find sine of x squared by plugging in x squared anywhere I see an x. So sine of x squared is equal to x squared minus x squared to the 3rd power over 3 factorial plus x squared to the 5th power over 5 factorial minus x squared to the 7th power over 7 factorial, and then continuing on. Okay. Not only do we know sine x expansion series, we also know the series notation for it, because it's another thing that we should have memorized. Okay, so we already know that the series notation, summation of n equals 0 to infinity of sine, is negative 1 to the n power times x to the power of 2n plus 1 over 2n plus 1 factorial. Okay, same thing we did with the series expansion is I replaced x with x squared. So I'm going to do the same thing here, which means this can turn into the summation of n equals 0 to infinity, negative 1 to the n power times x squared to the power of n plus, to the power of 2n plus 1 over 2n plus 1 factorial. Okay, I just swapped the x for x squared. And then I can simplify that by distributing the square inside the parentheses. Okay, which means this is the summation of n equals 0, infinity, of negative 1 to the power of n times x to the power of 4n plus 2 over 2n plus 1 factorial. So for this, it just says find the Maclaurin series. I showed you both the expansion and the series notation. Okay, so technically this is correct and this is correct. Okay. It's good to know both because on multiple choice, let's say all your answers were in series notation. You'd have to know the notation. Let's say all your answers were in expanded series, then you would have to know expanded series. Okay. If this was an FRQ, unless it states use this expanded series or use this series notation, either one would be an acceptable answer. So the hardest part here is just to make sure you have the table memorized. You have the table memorized, everything else is just plugging things in. Okay, any questions on 3? Okay, last one, number 4. Okay, so for number 4, it's x squared times e to the x. We already know the series expansion for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way x to the power of n over n factorial. Okay, this is what we have memorized. Well, if we want to multiply x squared by e to the x, that means every single term, okay, in this expanded series, we're going to multiply by x squared. So x squared e to the x is equal to x squared plus x cubed plus x to the 4th over 2 factorial plus x to the 5th over 3 factorial all the way to x to the power of n plus 2. Okay, because if we're multiplying this by x squared, it's adding 2 to the exponent all over n factorial. Okay, so again, I took 1, multiplied it by x squared. Okay, I took x, multiplied it by x squared. Okay, etc. all the way down the line. Okay. I could also use this with this series notation and say that the original series notation of e to the x is the summation of n equals 0 to infinity, x to the n power over n factorial. And if I was to multiply this by x squared, this would become the summation of n equals 0 to infinity of x squared times x to the power of n over n factorial, which just simplifies to x to the n plus 2 or 2 plus n, doesn't matter, over n factorial. So again, depending on what they're asking, these would be the correct answers.